Well, I see we have a full house, so we can take the liberty of starting a minute or two before the traditional 4:10. My name is Dick Karp. I'm the director of the Simons Institute, and I'm happy to welcome you to the second Simons Institute open lecture of this semester. And we're delighted to have Professor Emmanuel Candes as our speaker. Emmanuel did his undergraduate work at École Polytechnique in Paris. He then got his doctorate in statistics at Stanford in 1998, remained there for a couple of years, and then moved to Caltech, where he was on the faculty until 2006, when he returned to Stanford, where he's now a professor of statistics, mathematics, and electrical engineering. He's very famous for his work in compressive sensing and with applications to many areas of signal processing, imaging, inverse problems, information theory in general, optics, chemistry. It's an area that has really diverse connections, which makes his work especially interesting. Emmanuel was given the Waterman Prize in 2006. This is an annual award for the most outstanding scientist under the age of 35 in the United States, so it's a very important recognition of his work. He also holds the Simons Professorship, or the Barnum-Simons Professorship at Stanford. That's part of a program called Math Plus X, where the Simons Foundation recognizes outstanding researchers who bridge between mathematics and some application area. And today, Emmanuel is going to tell us about the effectiveness of convex programming in the information and physical sciences.
Okay, thank you, Richard, for this very kind introduction. It is a pleasure to give this open lecture, and I'd like to thank the directors of the Institute for inviting me. A few years ago, we also bid at Stanford for the Simons Institute. We were not successful. But retrospectively, it's a very good idea, I think, because then we can come to your beautiful campus, enjoy your beautiful center, without even having to run it. So it's just great. It's a pleasure to be here, really. So the topic of this lecture is the interplay between convex programming and the information and physical sciences. And to be honest with you, I don't have the skills nor the competence to give you a grand view of the interplay between these exciting disciplines. So I'm going to limit myself to tell you just 3 stories. And so, 3 stories, to quote from Steve Jobs, that's it. No big deal, just 3 stories from my recent work. And that's all we're going to do. Now, these stories are all connected through a theme. First, of course, the use of convex programming, but also the fact that we wish to recover signals or objects or data matrices from what appear to be incomplete sets of data. And so in story number 1, we're going to miss the phase of an image of interest. This is a phase retrieval problem. In story number 2, we're going to miss many samples from a large data matrix of interest. And in story number 3, we're going to be interested in recovering a broadband signal, but the problem is the completely high-end part of the frequency spectrum is completely missing. So the fact that we have all this missingness makes signal recovery difficult. Yet, and to me this is a bit of a surprise, what we'll see is that very simple convex IDs usually, always, not always, return the right answer. Okay, so I want to talk about the first story, which is about phase retrieval. And before I get started, I just want to mention that this is work with Yonina Eldar, Xiaodong Li, Thomas Tromer, and Vladislav Voroninsky, who used to be a graduate student at Berkeley and now at MIT. Okay, so what is the phase retrieval problem? It has its origin in X-ray crystallography. And X-ray crystallography, as everybody knows, is a method for determining the atomic structure within a crystal. And it works roughly as follows. So you've got a crystal of interest, let's say indicated by something like this, or more simply like this. what you do is you strike X-rays onto this crystal, and then those X-rays get diffracted. Right? So you have an X-ray tube that generates you collimate the X-rays, they strike the crystal, then the crystal diffracts the rays, and so you're going to get a pattern, a so-called diffraction pattern, and then you record the intensity of the diffracted ray. Okay, so we're discussing here very important areas of science. If you look at the number of Nobel Prizes awarded around X-ray crystallography, it's at least 10, and it may not be over. Okay, just to give you a sense, this is an open lecture, so a sense of the importance of X-ray imaging. This is, of course, a technique that was used to discover the double helix of the DNA, which arguably maybe is the most important scientific discovery after World War II. And so Franklin had made exquisite X-ray photographs, and then Crick and Watson used these exquisite photographs to infer this double helix structure. Okay, so what is the missing phase problem? In physics, we have to deal with the fact that detectors can only record intensity of diffracted rays. You have magnitude measurements only. You cannot sense the phase of the optical field, only its intensity. And so mathematically speaking, because when you do X-ray imaging, you're immediately in the far field, so I'm going to skip the details because I want to give you 3 stories, so we're going to keep the mathematical details to a bare minimum. But roughly what happens when you go and collect X-ray data, what happens is you have the object of interest, which is here an image of 2 variables, T1 and T2. The optical field here is simply the Fourier transform of the object that you wish to recover, but I cannot measure its phase, I can only measure its intensity, and so I just get to see the modulus squared of the electrical field. I cannot see the phase, and now the phase retrieval problem is an inversion problem, which is a century-old problem, extremely important problem in the physical sciences, is how can we recover the phase, or equivalently the signal, from the modulus of its Fourier transform. And of course, this seems extremely ill-posed because, well, you can impute any phase and invert, so we're going to have to talk about this. Okay, so just to show you the importance of phase information, we have 2 gentlemen, the 43rd and 44th President of the United States. And what I did is I computed the Fourier transform, and here they are. And now what I did in a sync, I kept the magnitude of the 44th president, but I impute the phase of the 43rd and vice versa. So I keep the magnitude, but I swap the phase. And then I invert the Fourier transform. I get something like that. And so what we can see from this simple experiment is that what every physicist knows, that the phase encodes most of the information. There is very little in the magnitude about the object you care about. So missing the phase is really a bad proposition. Okay, so X-ray imaging is a very active area of research. This is the first X-ray photograph ever taken by Wilhelm Röntgen. Of course, the first Nobel Prize for Physics discovered the existence of X-rays. What you see here is the hand of his wife with her wedding band, I think. And now you see that, of course, people are trying to image complicated stuff with X-rays. And for example, this is the kind of picture that people are trying to produce now. So X-ray imaging is a very exciting area of research that makes the cover of the most exciting magazines, such as Nature. For example, at SLAC at Stanford, there is ultra-short X-ray pulses that are used to try to image large protein complexes. And so what you've got is large protein complexes that fall in front of an X-ray beam, which is very short duration, high energy. And so what you do is you're blasting this molecule with this X-ray beam, and so you collect a diffraction pattern just before the molecule explodes, and out of these diffraction patterns, you want to recover a 3D structure. Okay. All right, so this is a mass or discrete mass center, so let's talk a little bit about the mathematics of phase retrieval. So mathematically, if I think about my object, and I know I'm taking a little bit of liberty with reality, but if I think about an object as being discrete, so discrete time or discrete space. So I've got an object which is in Cn, and yes, we can extend the result to the continuous world, and I'm not going to talk about it today. So I just want to keep things simple. So there's an object, which is the picture of interest, let's say the pixelized image of interest that lives in Cn. So I have n pixels, and I have got a magnitude and a phase. And when I do go through this kind of measurement process that we've just described, what I've got is I've got quadratic equations about the object of interest. So that is that I take my unknown object, I dot product with waveforms AK. So if AK is a sinusoid, this is exactly the experiment I described. I'm going to use a Fourier transform. But you cannot see the phase, so you just see the squared modulus. Okay, so the phase retrieval problem mathematically, it's very, very simply stated, is the following problem. Let's find an object X which is compatible with this quadratic equation. So it's really the solution to solving quadratic equations. Now, solving quadratic equation is NP hard in general. If you can show that you can solve any system of quadratic equations, then it says a lot about complexity classes. Let me show you a little bit what happens. So suppose you're in the real world, so everything is real valued. Well, you would like to see AX, but you don't see AX. You see absolute value of AX, you don't see the sign. So when I take a linear measurement, after a linear measurement, I would know that I'm on this plane or this plane, but now I don't know the sign, so I don't know on which planes I am. And then I take another measurement, and again, there's this ambiguity. I never know on which plane I am. It's a pair of symmetric planes. And I continue the data collection, okay, and I continue, and in the end, I've got these polytopes with exponentially many vertices. I know the solution is one of these vertices, but I really don't know which one. And I think that there is no algorithm known today that would work better is essentially find them, enumerate all vertices, and find the correct one. Now, if you over the real life, which is like now things takes place in are complex valued, then things are even more complicated because now instead of having pairs of planes, when I give you a dot x squared equals something, now I'm just talking about an algebraic surface. Okay, and so now if we're doing complex valued stuff, it's more complicated because each time I give you a measurement, you know that you're on an algebraic surface, and now you've got lots of algebraic surfaces, and you have to find their intersection, and that is extremely hard. Okay, so to go back to my previous slide, it's known to be NP hard in general. Now, it has not stopped physicists, of course, to try to find. It's such an important problem that you've got to find solutions. And so there was wonderful work by Hauptmann and Carly, who developed essentially Bayesian methods using prior information about what is it that we should cover. It's a crystal, after all, that you make very specific prior information about what is it that we're looking for, and they were awarded the Nobel Prize for their phase retrieval algorithm in '85. People don't really use it these days. People use instead, maybe I'm not going to tell you what it is, but they use the Gerstich-Saxton algorithm, which is an iterative algorithm that projects in data space, projects in physical space, projects in data space, and so on iteratively, that is not known to converge. And when you run it on real data, sometimes it works well, and sometimes it does not. And the literature is full of issues with this stuff. Okay. All right, so this is our phase retrieval problem. No phase, what are we going to do? Okay, so we're going to propose we need to bring convexity in this. So now, of course, it's not a convex problem. Of course, as you can see, the feasible set is absolutely not convex, so we're going to convexify it. And the way we're going to do this is we're going to use a technique where we're going to replace the unknown object, little x, a signal, by a matrix, capital X. Okay, so now I want to think about capital X as a matrix XX star. So it's a rank 1 matrix that happens to be positive semi-definite. Okay, and now the key observation is something like this, is when I take a quadratic measurement about little x, it is exactly the same as taking a linear measurement about XX star. Like there's a little bit of algebra that is trivial, it's undergraduate level, right? So basically what this is if I have my unknown XX star, then whenever I show you quadratic information about x, it is the same as giving you the dot product between the matrix X star and a rank 1 matrix, which happens to be AK star. Okay, so what this kind of lifting does to try to take the problem little on objects and mapping into the space of positive semi-definite matrices, it makes the measurement linear all of a sudden. Okay, everybody's with me? Yeah? Okay. All right, so we're going to take this point of view. And so in this world, what is the phase retrieval problem? It's very simply stated. When I think about it this way, it's an equivalent viewpoint. What I have to do then is I have to find a matrix capital X whose linear measurements are the data point I collected in the lab, is positive semi-definite, but I don't forget that this matrix is XX star, so it has rank 1. Okay, and so since there is a rank 1 solution, the phase retrieval problem can be cast as follows. It's simply the problem of minimizing the rank of a matrix subject to a section of the positive semi-definite cone. Okay, so when I've done this, I've not done anything. The problem is still NP hard. I just look at it differently. All right, so now most of you know what's coming. Is that, well, we have this rank constraint that is not friendly, so we're going to get rid of it and get something friendly instead. And so the phase lift that we propose with Yonina, Thomas, and Vlad is this following. It's like, let's remove this rank constraint, and let's do instead the following. Let's minimize the trace of X, which is really a proxy for the rank. So for those of you who know a little bit about sparse signal recovery, the trace is a sum of singular values, and the rank is a number of non-zero singular values. And so it's really the equivalent of L1 in the matrix world. So what we just do is we minimize the trace of X subject to the trace of AKX is BK and X. And so now I'm looking at something which is an optimization program, which is actually completely tractable. It's a convex optimization program. In fact, it's a special class of convex optimization program. It's an SDP, so this is a special class of convex programs for which we have good theory, good algorithms, and so on. And so all I've done is I've replaced the rank, which is not tractable, by its convex proxy, which is a trace. Okay, so this is a convex proxy for the rank. Right? That's a phase lift relaxation. Okay, so do we have people who don't know what is a semi-definite program? Maybe I'm not going to explain what it is. Just think about it, something that all of a sudden is amenable to computations. Like I can think, and in fact, since we kind of introduced this formulation, there's lots of people who have proposed algorithms for solving this fairly efficiently. Okay, so I'm going to skip that. And so now something a bit strange happens. Suppose I have 1,000 unknowns. So suppose X is of dimension 1,000. Maybe I have 4,000 equations. So now I was overdetermined in some sense, right? I had more equations than unknowns. Now they are not solvable, but I have more equations than unknowns. So I was overdetermined in some sense. And now I'm completely underdetermined. Because now I've got the number of unknown variables is X. Now I've lifted everything. So now the number of unknowns is N squared. So it's 1,000,000 unknowns. And I still have only 4,000 equations. So I've went from a completely overdetermined to completely underdetermined things. And so maybe I think things are terrible now. Because now I'm completely underdetermined. Okay. Now, this, of course, to people working in computer science, reminds you of the relaxation of quadratic constraints QPs. Okay, so introduced by Shor in '87, where he showed lower bounds on that you could use convex relaxations to get lower bounds on non-convex quadratic optimization problems. Of course, in the theory, in the literature on theory of computer science, there is this extraordinary papers of Goemans and Williamson, where there's a relaxation of max cut, and this looks similar to max cut. And then, of course, there's a lot of work about stuff like this. So if you look at the book of Ben, Tal, and Mirovsky, you'll see a whole section on convex relaxations of quadratically constrained QPs. Now, what is a bit strange here is that to kind of do this in the phase retrieval, it's a bit, first of all, it's a relaxation that's a bit different from what people do. But second, it's a bit strange to us that this kind of relaxation was never considered in the case of phase retrievals and problem like it in the physical sciences. Okay. But of course, in theory of computer science, people have been trained to think about it along these lines. Okay, so now, is this a good relaxation? So what can we say about this relaxation? So again, I've got these quadratic equations. And let's say that I want to solve a generic system of quadratic equations using this approach. And when I say a generic system, I'm going to assume, just because I want to keep it simple, that, well, I have generic random quadratic equations to solve. And so what I'm going to say is that the A's, they are uniformly sampled on the sphere. Right? So the rows of the matrix A, if you will, are uniform on the sphere. There is no preferred orientation. Okay, and we're going to try to solve this by the facelift approach. Okay, and there is this result, which we have established with Vlad and Thomas, and then later refined with Zhao Dong, which says something a bit strange. It says that if I have a number of quadratic equations, which is on the same order as the number of unknowns, n, then with very high probability, in fact the probability of failure is exponentially small in the number of quadratic equations, I can solve all phase retrieval problems by the approach I've seen. And in fact it's simpler than what I've just told you, because what the theorem says is that when I look at my feasible set, the set of matrices which are compatible with the measurements I have taken and are positive semi-definite, it reduces to a single point, which is xx star. So all I need to do to solve the phase retrieval problem from a number of equations which is exactly the same on the same order of magnitude as the number of unknowns is to solve a feasibility problem. I just need to find a data matrix X which is in the space of the measurement, compatible with the measurement, and is positive semi-definite. That's all I've got to do. I need to solve a feasibility problem, nothing else. Now, when I first discussed this result, well, there was some skepticism that it could be true because it goes a bit against intuition. First of all, let me just say that the number of measurements you need is at least 4n times minus 2, otherwise this mapping is not injective. Okay, that's a result of Edidin and his colleagues. And the reason is there was a bit of skepticism because, well, obviously there's a dimension mismatch, right? So you have very few equations, and how can have a space of enormous dimension intersect the positive semi-definite cone, which is a very fat thing, on only a single point? How is this possible? Because the pictures that everybody has in mind, at least the people we talked to at the beginning, was something like this. I've got the positive semi-definite cone, which is represented by the inside of this body, right? So this is a set of 2 by 2 matrices that are positive semi-definite. So in X, Y, Z, it would be the inside of this body. Now I have an enormously dimensional, an affine subspace of enormously high dimension. And what the theorem says is that they actually intersect in only one point, which is xx star. So obviously there's something wrong with this picture. So what is wrong with the picture is that the world does not look like this in high dimensions. And so I don't know how to draw a correct picture because now we have to deal with high dimensional phenomena. And so I'm just going to tell you what is in my mind, and we'll see whether I'm successful in communicating the only thing I know really. So now what you do is you take a matrix which is xx star. It's a point in a very high dimensional space. And now I'm trying to perturb it. Now the perturbation, to be feasible, needs to be positive semi-definite. Now if I take a rank 1 matrix and I perturb it by adding a symmetric matrix and I say, add an arbitrary symmetric matrix, do you maintain positive semi-definiteness? No, because you had one positive eigenvalues, all the other one was 0, you add something symmetric, so some eigenvalues will become negative. So by moving in this direction, you will not maintain positive semi-definiteness. Take another perturbation. You will not maintain positive self-definiteness, and so on, right? So almost all perturbations you can think of will take you outside of the positive semi-definite cone. So the picture I've got is that really the positive semi-definite cone around a rank 1 object is extraordinarily sharp. So it looks like this, right? So I've got xx star, and then the set of feasible directions is extremely narrow. And now I take a very large affine subspace that has to go through this point, and I say, where is it going to intersect the positive semi-definite cone? And it's going to intersect in only one point, which is this point. Right. And so the reason the phase retrieval by semi-definite programming works is because the positive semi-definite cone is extremely sharp around low-rank objects. Okay. All right. So, well, you'd say, what does my model have to do with physics? Because I assume that the equations were random. In fact, you can extend this work. And now this is joint work with Thiel Xiaodong and Madi Soltanol Kotabi, where we showed, well, what you could do to do the phase retrieval is to do something like this. You shine your X-ray source on your molecule, and then you encode it by putting a phase plate. So this is like a binary mask, if you will, and then you let the thing diffract. Each time you change your mask over here a few times, you collect a few diffraction patterns. Now you have quadratic equations that are now physically realistic. And what the theory says is that this works as well. Okay, so this works not only for idealized models, but also for things that are a bit close to what you might be interested in practice. Okay. All right, so when you do this on data, it works reasonably well. So what we did is we implemented code and stuff to solve the phase retrieval problem in this setup by just finding a feasible point. Okay. And so in blue here you see a signal, and in red you see the reconstruction, and you see that they're exactly on top of each other because the semi-definite program gives you exactly the same answer. And since I make no assumption about the signal, it doesn't matter whether the signal is kind of smooth like this or random like this. It really doesn't matter because it's all about the encoding process and not about the input. And so what you see in practice is that typically we have when you implement the semi-definite programming idea, so if you have a signal with n components, n blocks of information, which is complex valued, so you have really 2 n unknowns, if you give me 6 n measurements, that's enough. Like, so I can recover, or we can recover arbitrary signals with 2 n unknowns from about 6 diffraction patterns. You need at least 4, and with 6, this seems to work. Okay, now the good thing about convex programming, which is a theme that I'm going to silence a little bit in this lecture, is that, well, it's a model-free method. So now, in fact, in real life, the data is not going to be exactly x.ak because you're going to have noise. So you're going to have, let's say, a Poisson statistic. And so what you say is, well, in general, what I'm going to do is I'm not going to solve the feasibility problem. I'm going to try to find a point, a matrix X, which is as close to B as possible in some sense, by perhaps maximizing the log likelihood or do things like that, subject to X positive semi-definite. If you get a solution X which is not rank 1, just take its rank 1 solution, and that's your signal. And the statistical theory would say something like, well, you can't really do better than this, really. I mean, if you do this, then there's no method that can essentially work much better than this. Okay. All right, so the thing is that maybe I'm going to not talk to you about the statistical theory. I think what is convenient with convex programming is when you have approximate data, noise, and so on, it goes through the same machinery, and you get stable recovery, meaningful results. This is a very boring plot, but we were very happy when we saw it. It's very, very boring because what it shows a relative mean squared error in dB, so on a log scale, versus a signal-to-noise ratio on a log scale. And what we see is as a signal-to-noise ratio increases, a mean squared error decreases in a very predictable fashion. Okay, and so what that's saying is each time your signal, the noise level goes down, then the relative MSE goes down. And so what you have is you have the kind of plots you would get if you were to solve a well-posed least squares problem. Okay, so it has, even though the generation mechanism, you don't have a linear model, even though you have an absolutely nonlinear reconstruction method, everything behaves as if you were solving a well-posed least squares problem. Okay. And so you can apply this to real data, and we have, courtesy of Stefano Marchesini at LBL, and so you can get pictures of gold balls if you want to. All right. Okay, so that was my story number one. Should I take question about story number one now or at the end? Or? Yes.
So what happens when you do that to rock bombing where can you recover? Does this technique allow you to recover the original pictures?
Yeah, as long as I've got quadratic equations that are sufficiently randomized to some extent, you can, yeah, of course, yeah. Yeah. I mean, there is a theory, yeah.
Speaking of computer science, what's the status of implementation of this, and the scalability?
Right, so this I will answer at the end, because I think this is a theme that we're going to see several times. So, yeah. Okay, so let's now move on to story number two, also connected with a missing data problem. And now it's work with Emma and John Wright. They are wonderful computer scientists. John is at Columbia, and he is at Microsoft Research in Beijing. Okay, so we're going to talk about a completely different problem now. And the problem is inspired by now not physics, but problems in data analysis. And I'll tell you where it's coming from in a minute, but right now the problem is as follows. There's a data matrix M that you get to see as a statistician, which is a sum of a matrix L, which is low rank, which is essentially pictorially represented by something like this, and a sparse matrix, which is something like this. Right, so the low rank part is not observed, and the sparse part is not observed. What you get to see is the sum of the two. Okay, and the question that we would like to ask is, can we recover L and S accurately? And again, it seems that we have a terribly missing data problem. Well, how many unknowns do I have? Well, 2 times the number of entries. How many equations do I have? Well, the number of entries. It seems like it's not right. Okay. Now, why do we care about this? At least my motivation, and you'll see that there was another team working on this completely different motivation. My motivation was robust PCA. So, everybody knows what is principal component analysis. We have a data matrix. This is point number 1, point number 2, point number 3. So we have columns in a matrix, and we like to reduce dimensions. So we assume that these columns lie near a low-dimensional subspace. And so if I can only plot in the planes, if these columns were lying near a one-dimensional subspace, where I were to plot them, it would look something like this. And so if I run PCA, I would get the low-dimensional structure very, very well. But now suppose that maybe there's a corruption point in this data matrix. There's one entry that has been on purpose, or maybe not on purpose, incorrectly recorded. Right? So this point that was plotted here in blue, because this entry is incorrectly recorded, happens to be here. Now I run PCA, and truth is this is the first principal component now. So if I have one corruption, the first principal component are completely off. They may be completely off. Right? So one thing we don't talk too much when we talk about statistics, when we teach multivariate statistics, that really principal component is very sensitive to outliers. Right? It's an L2 technique, so it has to be sensitive to outliers. And the problem is that now when we deal with big data, high-dimensional data sets, we cannot ignore the fact that we're going to get many problems like this. Why? Because If I work in computer vision, I have occlusions that introduce some sort of errors. If I deal with sensor nets, sensors will fail, and so I'm going to have ratings that are unreliable. And if I deal with other kind of data, again, people may enter bogus entries on purpose. Apparently, this is a case of Netflix, which I'm not going to, I think people know what is a Netflix price. But one day I was talking to people working on the Netflix problem, and they told me this. They said that, well, you know the Netflix price, we get a few ratings by users about movies, and they said, you know, in this Netflix data, there are entries that are not reliable. There are people who enter bogus ratings on purpose. And so if you look at the Netflix price, and as you know, the winning solution is essentially 80% of a low-rank model, is that you get samples now of a low-rank component, which we think of as being the true matrix of users' ratings, plus a sparse component, which would be corresponding to those entries that have been tampered with. So we wish to recover a low-rank matrix from a sample of corrupted entries. Okay. All right, so now there are other applications of the L plus S model, and I mentioned this other group of Chandrasekaran, Shangavi, Perillo, and Wilsky, the MIT group, where they got very interested at the same time about this low-rank plus sparse model by working on a very beautiful application having to do with graphical models with hidden variables. A fantastic line of work. Okay. So again, we wish to solve this underdetermined problem of a very different nature now compared to the phase retrieval problem, where we have a data matrix. Again, it's a sum of a low-rank plus sparse component, and I'd like to separate both components. And that is, well, it seems to be a bit problematic. So what do we need, first of all, to make this thing kind of have a chance to succeed? Well, these problems need to make sense. So, of course, if M, the matrix you give me, is both low-rank and sparse, so for example, if M is something like this, then this problem cannot make sense. I cannot separate this matrix into a low-rank component and a sparse component because, well, the low-rank component could be this and the sparse component could be 0 because this matrix is both low-rank and sparse. Right? Okay. And so if you give me a matrix that looks like this, I could say, well, the low-rank component is this, the sparse component is 0, or you could say the low-rank component is 0, the sparse component is this, and or half and half, and it doesn't really make sense. And similarly, the sparse component cannot be low-rank for exactly the same reason. Okay. So what is really underlying here, and that maybe we should think about the Netflix problem a little bit. So if the rows of the data matrix are users and the columns are movies, what allows to do matrix completion or correcting errors is the following. That is, if I've got the true matrix, the true low-rank component has 2 rows, which may be the same, by the way, and everything else is 0. And now I corrupt these 2 entries. Or, for example, I even tell you which entries I corrupted, so you would know that these entries and these entries are reliable. How are you going to be able to impute what I corrected? Right, so if these are preferences for movies, and there's Mickey and myself, there are movies we like. All the rest of you like nothing, no matter what. And Mickey's rating has been corrupted for a movie. My rating has been corrupted. How can I impute Mickey's rating for this movie? I cannot. Because what I would need to do is I would need to use other ratings that are of people are similar to Mickey and myself to detect that this is an unusual rating, correct it, and impute the correct value. So in this line of work, for matrix completion or robust PCA to work, we cannot have rows or columns that are singular in the sense that they are orthogonal to everybody else. Okay, and this is captured by a mathematical condition that we worked out with Ben Recht, who is now here at Berkeley, that I'm not going to discuss. But basically, I want just you to get the intuition that, well, if I have a matrix that looks like this, that have, say, a pair or a row or two rows that are singular orthogonal to everybody else, there's no way I can correct corruptions or even impute missing values. It's not possible, because I cannot borrow from the experience of others. Okay, so, and similarly, if you're very adversarial with me, if you give me a matrix which looks something like this, it's nice because it's a rank 1 matrix, everybody looks exactly the same. But if you go out and corrupt the first column, right, you see X1, here it's a rating for a movie, and you corrupt all the ratings for these movies, and there's no way we're going to see whether we're going to like it or not. We don't even know what this movie is like. Okay, so mathematically, there is no information about X1. It's all gone. Okay, so we're going to assume that in this model that, yes, you can corrupt, but the corruption, what we're going to do is you can corrupt. So what I'm going to let you is I'm going to select a fraction of the entries at random. So you're going to have access to a random set of entries, which is of cardinality proportional to the total number of entries, and you can do anything you want. But I'm not going to let you corrupt things in a structured fashion like this. All right, so now we've got this demixing problem where we observe the sum of a low rank and a sparse matrix. And again, we don't know much about L, we don't know much about S, we don't know the rank, we don't know how many entries have been corrupted. I have no idea about the locations, the magnitudes, all that. All of this is unknown. Okay, and so now to kind of recover this, okay, so there's this paper, again, this MIT paper and our paper. The proposal is identical in both papers. We're going to try to minimize, again, do this by convex programming. So among all the compositions that give you the observed data matrix, so we're going to find an L and an S. And so we both want to reproduce what we've seen. But then we're going to try to favor low rank and sparse components. And so how do we do this? Well, we're going to try to make the low rank component as low rank as possible. So we're going to use a convex proxy for the rank. The rank, as you remember, is the number of non-zero singular values. So just going to take the L1 norm of this, so the sum of the singular values. And for the L1 norm, we're going to use what people use everywhere. We're going to use the L1 norm of S seen as a big vector. Okay. Again, this is a convex optimization program. This is a norm. This is another one. So I'm summing two norms. I'm convex. In fact, it's an SDP. Okay, so we just do that. All right, and so what is the main result? So we solve this optimization problem. It's really completely straightforward. Note that I don't know maybe we're going to discuss the tuning of lambda, but other than that, I've got nothing. I don't need to know the rank or the number of entries that have been corrupted or their locations, nothing. I just minimize this. And the result is a bit surprising. Is this, suppose M is the sum of a low-rank matrix, which is what we call incoherent, that is, does not have rows and columns that are orthogonal to everybody else. Suppose you corrupt it at the positive fraction of entry, so each entry has the positive probability of being corrupted, let's say 10%. Then with enormous probability, so the probability is over the locations of the corruptions, this optimization program, when you plug lambda equals 1 over square root of the dimension of the matrix, is exact. That is, when you inspect the solution to your SDP, the low rank is exactly the truth and the sparse is exactly the truth. Okay. And this, I stated it for matrices that are squared. If matrices are not squared, the result is exactly the same. The only thing is how do you pick lambda is 1 over square root of the maximum dimension. Okay, so this is a bit bizarre because what it means that you have a low rank matrix and then you start messing around with lots of entries selected with locations selected at random. You give me this matrix and I solve this naive optimization problem that has no tuning parameter because I just plug lambda equals 1 over square root of dimension. And no matter what you did, I will identify all these locations correctly, remove the entries, and put back the low-rank solution. Okay, so it's a bit of a bizarre result that shows that I can demix the sum of a low-rank and sparse matrix. Now, when you run this in practice on random problems, you see something like this. So on the x-axis, you see the rank of the low-rank component divided by the dimension. So if you see 0.1, it means that the rank is n over 10. And on the y-axis, you see the fraction of entries that are corrupted, which is here, you see, like I messed up 20% of the entries. And we generated random low-rank matrices, random sparse corruptions, and then we run the algorithm, and we counted how many times we got it right, how many times we got it wrong. And if we got it right 50% of the time and wrong 50% of the time, you'd see a gray pixel. But you do not see a gray pixel in this figure. What you see instead is you see what people call a phase transition, which is that in this area, the algorithm always succeeds, and in the one it fails. And so what that means, it means if I have a rank matrix of rank n over 20, so I would be about here, that is being corrupted, what this theory says is that you can corrupt about 35% of the entries and still be fine. And beyond that, you don't know. Okay, so now you say, well, what if you have corruptions and missing entries? And again, that's the flexibility of convex programming. You say, well, I'm going to do exactly the same, except that I'm going to enforce data constraints only when you give me samples. So now the problem is really Netflix. That is, you've got some samples in blue that are indicated. Of course, you have some of these samples are corrupted, but nobody tells you which one they are. So because nobody tells you which one they are, you cannot discard them. So you fit an L plus S model like this. Okay, and you've got the same result. That is, if you choose lambda to be whatever it is, then this succeeds exactly. That is, you would actually detect those corruptions, replace them, and fill in all the correct values without having to do it. Really, you just look at L hat. That's all you do. Okay, so when people use this to do fun stuff, to do background subtraction, so here is it's not our work. Oops. Okay, so this is a video that is done by a group. They use this low-rank plus sparse decomposition to do background subtraction. So you have a video sequence. You want to separate the background from the foreground. The modeling assumption is that if I look at each frame of this video sequence as a column of a data matrix, the background is not changing, so it's low rank, and the foreground is a sparse disturbance in this low rank background. And so when you just apply this L plus S decomposition out of the box, you get something like this. This is a movie from not our group, but we have movies like this, but I'm showing you work of other people now. So this is the original scene. This is a low-rank component, and then the sparse component is just picking up the people moving about stuff in the background. With two researchers, Ricardo Tasso and Daniel Sodiksen, we apply the L plus S model. The L in a dynamic MR sequence that is in a sequence of images with time is going to have a static component, which is well modeled by a low-rank element, and a sparse component, especially in angiography, which is well modeled by a sparse matrix. And so we're using this L plus S model to do recovery of the contrast that is flowing through the veins automatically from undersampled data. Okay, and so you don't have to do background subtraction. It's all built in, and so on. And so with Ricardo and Daniel, and maybe I won't talk too much about this, but what's interesting, so Miki Lustig has been done fantastic work at promoting the sparse model for MR. And so now we're looking at the potential offered by a low-rank plus sparse model for dynamic MR, by modeling both the static component as a low-rank component and innovation as a sparse component. And so I'm no expert in medical imaging, so I would not know how to judge these images, but from what Ricardo and Daniel tell me, they're pretty happy about the use of the L plus S model to get sharper video sequences. Okay. If you have noise again, well, you don't enforce exactly equality constraints, you relax them, and you have theory that would say that you have stability. Okay, so it's the end of story 2. Do we have questions at the end of story number 2?
So I had a question. The sparse component, was it the case that the locations, the non-zero entries in the sparse component, the locations were random, but the entries themselves were scarce, adversarial?
Yes, so the locations are random, but the entries can be adversarial, yes.
So when you prove the theorem about it, that's the model, right?
Yes. Okay, so my last story about convex programming has to do with super resolution, and now I'm going to go a bit faster. This is joined with a graduate student, Carlos Fernandez Granda from Stanford EE. So, well, I'm going to pick up a bit. So, as you know, well, if I have a point source in the real world and I'd like to image it, whether I do astronomy, microscopy, photography, a point source will not appear as a point source. It will appear as a point spread function, something that looks like this. Everybody's with me, I suppose, right? Okay. And it's because of diffraction. Okay, so maybe I'll go very quickly about this, is that if you look at an imaging system, there is an object F that you care about. You'd like to image it, but you can't. What the microscope can do, it can recover the convolution with F and the point spread function. And this, in the Fourier domain, a convolution becomes a multiplication. And so in the Fourier domain, what this is you're multiplying the Fourier transform, the spectrum of the object, by the transfer function. And so most optical systems have the following property, that there is a frequency cutoff, and the transfer function is 0 after the frequency cutoff. So you do not see the high frequency component. Okay, and so if you look at a camera, like the transfer function would be like some kind of an indicator of a disk that have to do with the pupil of your object, or the point spread function will be the so-called airy disk. And so what that means is a point source will appear like this on your photographic plate or on your CCD array. Okay. All right, so something like this appears something like this. When I look at the distance between the peak of the transfer function and the first zero crossing, it's called the Rayleigh distance, introduced by Lord Rayleigh. And so, roughly speaking, the physical interpretation is this. I take 2 point sources and I bring them close, and at some point, they will appear at just one bump, not 2 bumps. And the distance at which they appear at one bump is called the Rayleigh distance. All right. So the objective, the super resolution problem, at least this super resolution problem, people talk about in optics, is this. That is, I'm interested in this. I'm interested in resolving those point sources, but I can't see them directly. I just get a low-pass version of it. And so the problem is to go from here to here. Now I can think about this in the Fourier domain instead, where, well, this has a spectrum. So this has a Fourier transform, which is these wings. But because of the optics, I can only get information about the low frequency, so I get to see this red part, but not this, and I need to extrapolate the spectrum. Right, so this is really the super resolution problem. It's extrapolate the spectrum. Now, as you can see, if I have a superposition of of point sources, it has a lot of mass in the wings. It's not a low-frequency object. All right, so this is very different from compressive sensing. In compressive sensing, what you do is you use randomness to undersample the spectrum, but you can do it wherever you want. Here you're constrained by physics, where you can only see the central part of the spectrum. So compressed sensing is really a problem about interpolation. Super resolution is very different. It's a much more nasty object. It's a problem about extrapolation. It's very different. CS is interpolation. Super resolution is extrapolation. Okay, so maybe there are many people who try to kind of resolve point sources. Well, if you work in astronomy, you're interested in celestial bodies, so they would be point sources. You have line spectra in speech analysis, fluorescent molecules in single molecule microscopy. And so, for example, we work with the work of the lab of W.E. Murner, who is a chemist, a single molecule specialist. And so he's interested in imaging single molecules which are way below the diffraction limit. So they appear much fatter than they are. And so what you'd like to do super resolution to locate them very precisely way beyond the diffraction limit. Okay, so this is now like the third problem and the third convex solution we're going to look at. And then I'll stop. So now I've got a signal, and I have a superposition of point sources. And so I've got objects at unknown locations with unknown amplitudes, perhaps complex valued. And all I know about this, the optics, what the optics is giving me low-frequency data about these objects. So all I can measure are the first Fourier coefficients of this signal. Right? So I measure, in each coefficient I have, these are low-frequency Fourier coefficient of this. And so that's all I get to see. And because I've got a frequency cutoff, so I can only see those wave numbers below a cutoff location, log Rayleigh comes in and it says, Emmanuel, you do not have the right to think about a resolution which is below 1 over the frequency cutoff. This is the Rayleigh distance. There is no information beyond this limit in the data set. Yet, we would like to go beyond because we need to resolve these sources beyond the diffraction limit. Okay, so here is what thing you might see in practice. This is a convolution of point sources with a sinc function. And so now I'm asking, where are the sources? This is a problem you need to solve. And, well, the left plot has 3 sources, and they were here. And the right had 7, and they were here. And that's what you need to do, to go from the blue curve to the location of these sources. Okay, and of course, here you see something like your Rayleigh distance. Now, how are you going to do this? You can do this by algebraic method, but it's a lecture about convexity and convex methods. So we're going to do this by convex programming. And what we're going to do is we're going to do something extremely simple. We're going to use the L1 analog, but in the continuous world. So I'm going to use the total variation, now the total variation of the probabilist, the metrics they use to measure distance between probability distributions. And so all I'm going to do is I'm going to try to say, well, I've got few Fourier coefficients about an object, which is like this, like this. Think about really what we're looking at is if these were not trigonometric polynomials, but just moments. It's like how do you recover a measure from its moments? It's really the same thing. Okay. All right, so you give me a few trigonometric moments, or a few moments of this measure x, this sine measure x. And what I'm going to do is I'm going to try to find that measure with minimum total variation. And the total variation is very simply defined. It's simply, well, what is the total variation of a sum of amplitudes, point mass at delta tau j is simply the sum of the amplitudes. So it's really, I'm going to go a bit faster now, it's really in the continuous world L1. It's a continuous L1. And if you give me noise, well, I'm going to trade off between data fidelity, or perhaps with a log likelihood term, and this continuous L1 norm. Okay, so now you have this, and the result is like, here is your third convex program, and the result is this, well, if the spikes are separated at a distance which is twice the Rayleigh distance, then this optimization program that just simply minimizes the titral variation, that does not know that you're actually searching for a sparse spike train, is finding exactly the right spike train. So the theorem with Carlos says if the spikes are separated by twice the Rayleigh distance, then this convex optimization gives you the right answer. So it's going to locate from just a few moments, from data that looks like this, the location of these spikes perfectly. All right. So now you'd say, well, but how do you do this? Because now you are over the continuum, so now you have a continuous optimization problem to solve. How can you implement this on a computer? Okay. And maybe I'll skip my stuff. That will be it. So what you want to do is you want to minimize the total variation norm subject to equality constraints. This is a convex program, but the problem is that now the stuff you're looking for is infinitely dimensional. It's over the continuum. So how are you going to do this? You have finitely many constraints, but the unknown object has infinitely many variables. Well, every program has a dual, and the dual of this thing is something like this. What you want to do, so it's really like duality in linear programming, what we're doing really. We're not doing anything fancy. The dual of this optimization problem is you want to maximize the real part of the dot product between the data vector y and a coefficient vector c. So your dual optimization variable is c now, subject to fn star, the adjoint of fn, less than 1. So now what does this mean physically? It means that I need to find the coefficients of a trigonometric polynomial, c, such that the correlation between these coefficients and the data vector is maximized. Right? That's a dual. Now when I do this, there's conservation of difficulty because, well, I had infinitely many variables. Now the good thing in the dual world is it's a finite dimensional problem, but I have infinitely many constraints. Now it turned out that there is a result which is essentially a result of Kalman, I believe, and Popovich and others, that this is actually semi-definite programming SDP representable. Right. So searching for the set of coefficients c such that a trigonometric polynomial with coefficient c is in magnitude less than 1 over the whole interval 0 to 1 has a semi-definite programming characterization, and I think it works again, it goes back to the work of Kalman. It says that it's equivalent to this, is that there is a matrix Q which is Hermitian, such that the matrix Q C star 1 is positive semi-definite, and Q has additional structure, its trace is 1, and its sums, when I sum Q along superdiagonals, they vanish. So now, how do I can solve the super-res problem? I just do this. Well, the dual problem is formally equivalent to this. It's exactly the same as this. So now it's a finite dimensional problem. I can use CVX from my colleagues Michael Grant and Steve Boyd. Okay, so I just solve this SDP, and I get a trigonometric polynomial C. And I look at it, and when the trigonometric part takes the value plus or minus 1, this is the support of the signal by complementary slackness. And so if I want to recover the spike locations, I just look at when this trigonometric polynomial takes the value plus or minus 1, this is exactly the support of the signal. Okay, and so when you work on this on data, so here are low-pass measurements about a spike train with an SNR 14 dB. This is a data. This is what you would like to have. This is really a perturbation of the result signal. And now you solve the perturb SDP with the data feeding term. Okay, this is where the signal is, but that, of course, you don't know. What you just get to see is just this blue curve. You solve your SDP. You look at the values where the trigonometric polynomial takes the value plus and minus 1. That's your signal. And when you do this from noisy data, you can see that when the noise level is not high, you get a very accurate localization of your spikes, of your sources. Okay, so I want to kind of conclude saying that in this lecture, what I've tried to present is, I think, 3 important problems with missing data: phase retrieval, matrix completion of robust PCA, super-res. That somehow, if you can invoke ideas from convex programming that make essentially no modeling assumption, they're model-free, and they give you a very good solution. Not always a good solutions, but oftentimes you get very good solutions. And then I really sinned because I did not talk to you too much about algorithms. There was a question about this. Applications I've shown you are just an idea of what they could be. And there's an avalanche of related works. And so my last slide would be to try to encourage you to work and read papers by some of my colleagues who do spectacular work in this area. I mentioned the great work of the MIT group. For those of you who are working in computer science, of course, there's a deep connection between phase retrieval and max cut and graph cut algorithms. There's a nice paper by Walzburger making this connection. There's a lot of stuff happening in this field. It's a good area because, as you said at the beginning, you can do some theory and then connect it with applications. And I thank you very much for your time. If people want to ask questions or...
Take a couple of questions if you have them.
So it looked like in the last plot you showed about the localization, that the localization was substantially better than the estimation of the values.
Because it's an L1 method, so there's a self-thresholding effect. And so, yeah.
And do you have theory about how well it does the localization with noise?
There is, if you look at the papers on noisy super resolution by these ideas, you'd see the beginning of it, but it needs to be still. It is in its infancy.
I mean, doesn't that stuff go back to about 1989, the Donahoe and Stark work on...
By semi-definite programming?
By L1 minimization?
Okay, so the super-res, so Donahoe has a few papers. So I mentioned, so on my backup slide, I have work of Donahoe here. I don't think so, because I don't...
The 89 paper.
Yeah, but I think it's quite different, though, because first of all, here we are on the continuum. Oh, excuse me?
One version of that, the theorem in the 89 paper is in the continuum.
Okay. So it's possible then. I'd have to look, because I know your work very well, T times W less than N. And so, but I was not able to make a direct connection with your work. But I might want to revisit this.
I haven't thought about it more.
The result you mentioned, so Donahoe and Stark, so this is Phil Stark, have a very important paper that kind of showed what L1 could do for spike recovery. And the model, if you allow me, was, so you had a sparse spike train, right? And then you had an assumption that says that if the size of it was all discrete, and if the size of the support set times the size of the W was less than N or something like this, then L1 would work, or square root of N or something like that.
There are several different versions in there, and really, I haven't thought about this in decades, as you know, but one version is like that. Another version is you have a band-limited signal corrupted on an arbitrary set of small measure, and you recover with L1 perfectly.
Yeah.
And then there's also some theory in there that suggests that provided the sets are thin, so you have something like sparsity rather than total measure, that it should still work. That anticipates the Donahoe and Logan results from the early 90s that went further in that
Right. So I actually have studied personally all these works. It seems like when I look at your work and the work of Donahoe with Logan and the work of Donahoe by himself, which is the work I'm mentioning here, which is the closest for super resolution via sparsity constraints, there is in this work this is, I think, in my view, the one that comes closest to what we do, because it's really looking at the problem of super resolution, which is, I think, a bit different from perhaps your earlier paper. And the work of Donahoe, so let me mention what it says. The work of Donahoe shows the following, that if I take if the density of spike per Nyquist interval is grows at a certain rate, then the ill conditioning of the problem grows at a rate that depends on the density of spike per Nyquist samples. But you have infinite amount of data, if I remember correctly, and this is just a modulus of continuity calculation, and there was no formal proof or formal way of saying what happens if you try to solve the continuum L1 problem. So, but I'm happy to go back to your paper. So the work I know is the work of David Donahoe, which we refer to extensively in our paper, that looks at the modulus of continuity for super resolution, where he shows, contrarily to what people might think, that super resolution may not, under sparsity constraints, may not be as ill-posed as people might think.
Well, let's take the discussion offline at this point. Thank you again.